Alicia Couto. I'm researcher from CONICET and also professor from the Buenos Aires University. And I also belong to the CQBM, that is the facility of mass spectrometry from the University of Buenos Aires. Well, just to remember, for those who are not so familiar with this, we had two types of mass spectrometric techniques. One may be MALDI, Pia today remember us. It is a laser desorption, matrix-assisted laser desorption ionization system, where you put a solid sample analyzed with a photosensitive molecule that is called matrix, and the energy passes through from the matrix to the analyte, and they produce the desorption and ionization. Then the ions are separated and detected in this is the mass spectrum. In this case, this type of mass spectrometry technique is very useful for mixtures, because they nearly always you have monocharged ions. In the case of electrospray ionization, you see here is the tip that is kept at a high voltage, and the liquid sample, the solution of the sample, passes through the tip, and it is spray and ionized, and these ions are separated through mass charge relationship, and you have this type of spectrum. In this case, electrospray produces multi-charge ions, and so it's not so easy to use for mixture. But it is very often coupled to an HPLC, and so you can separate some mixtures in the HPLC and then analyze them by mass spectrometry. Well, so if you have a glycoprotein, I'm just showing you a workflow to remember how to work with this. In general, it's very common to work with a gel band, because having a purified glycoprotein is not easy, as we have seen today. So we have an isolated glycoprotein in a gel band. You stain it and you cut the gel band. And this gel band may be digested in gel with, for example, PNGS enzyme. This enzyme cuts the N-glycosylation part of the glycoprotein, and so you can extract the glycan. This is a glycomic approach. You study only the glycan. You have the glycan. You may identify and characterize it by mass spectrometry and also by HPLC. Another type of approach, well, you may also have the protein that you keep it in the gel and then perform an ingel-trypsin digestion and analyze the peptides by mass spectrometry. Another type of approach is to take the gel band containing the glycoprotein, and directly these glycoproteins perform an ingel-trypsin digestion. So you will have glycopeptides and peptides. That is a glycoprotein approach. And you may enrich a fraction with glycopeptides and then perform a mass spectrometry analysis of these glycopeptides. Of course, you can perform a protein identification with data bank, and you may characterize glycopeptides. So, I am just going to show you two examples of different glycoproteins. In this case, we studied the less layer glycoprotein from Alopherax volcani. Alopherax is an archaea. It was first isolated from the Dead Sea. And archaea glycoproteins are known to be very much N-glycosylated. So when someone took us this problem, the S-layer glycoprotein has 7 putative N-glycosylate sequence, and there were a lot of work being performed before, and for example, asparagine 13, asparagine 83, asparagine 484. It was already known that they were glycosylated and the type of glycosylation. And also they knew that asparagine 370 was not modified. But what about the other sequence? And so what we did was to perform first an SDS page. We analysis, we stain it with silver nitrate. Here is the band corresponding to the molecular weight, and we pass for carbohydrate, and you see here the carbohydrate. So we took this band, we sized the band, and we treated with N-glycanase or PNGSF, it's the same enzyme, and analyzed the released oligosaccharides by anion exchange chromatography. And in this case, we obtained a lot of peaks that were released with the enzyme, but they were not like the general structures known for N-glycoproteins. So we first took this mixture, and looked for the monosaccharide components. And when we made acid hydrolysis, the hydrolysis products were analyzed by anion exchange chromatography and also by MALDI. And so this was the analysis in anion exchange chromatography, and we could detect a big peak of D-glucose and also a peak of that migrated less than 3-O-methyl D-glucose that was suggesting modified sugar, and also a little peak of glucosamine, a little peak of mannose, and a high peak that was not known. So we took this fraction and analyzed it by MALDI mass spectrometry in the linear positive mode with normal as matrix. And in this case, we could detect, for example, little pieces that corresponded to methylated exos, and this piece was characteristic of a sulfokinogos exos, and this peak to a methylated sulfokinogos linked to an exosamine, and this peak with the same structure but with more an exos, and this with 2 exoses, and this with more methyl groups. So with this knowledge, we performed the MALDI analysis of all the oligosaccharides released with the enzyme. And in this case, we could detect 3 clusters of ions. The first cluster corresponded to 2 exosamines, sulfokinogos methylated, and this also had other ions that corresponded to different number of methyl groups to the same structure. This structure had been already determined in other glycoproteins from Archaea, so it was not so bad. And when we passed to the other cluster of ions, we obtained the same structure but with 1 hexose more. And in the third cluster, another hexose more, and also with different number of methylated methyl groups substituted. Of course, we took each of them and we performed an MS-MS analysis. I'm just showing this peak, the MS-MS, that's corresponding to this peak, and you can see that, for example, this part corresponding to this peak, and also this part corresponding to this peak, and this part, each little piece of the structure could be detected in the MS-MS analysis. So from that analysis, we could assure this structure for the oligosaccharide. Further on, we perform a MALDI mass spectrometry analysis, but now in the linear positive mode of the released oligosaccharides by the enzyme. And then we could detect the corresponding ions, but in this case we could detect a higher mass ion that could be, after MS analysis, detected as the same structure but with repeating units of methyl sulfokinurose exoses, like this. So we could say that a new oligosaccharide with this structure, 2N-acetylhexosamine, 2 exoses, and a repeating unit of methyl sulfokinurose exos was the structure present in that glycoprotein. It's very rare, but it is from an archaea, that's different. So the next step was to see where was this glycan linked to. And for that, we performed a glucose digestion of the gel band. And in the glucose digestion, we could detect different glycopeptides, some of the ones that had been already determined, but one that could be detected that corresponding to the asparagine 732 and bearing a piece of our already detected oligosaccharide. Of course, we perform a mass analysis of this and of this ion, and we could detect different pieces of the peptide bearing the oligosaccharide. And so we also perform a trypsin glucose digestion of another gel band in order to be sure, and we could detect signals corresponding to the same site and asparagine bearing the pieces of the oligosaccharide. So up to this part, up to this point, we could say that to the known glycosylation sites, we could add another glycosylation site, N732, bearing this new oligosaccharide. Bearing this new oligosaccharide in this point. Well, all this work was performed with MALDI. I'm going to show you another S-layer glycoprotein. This work was with Lactobacillus kefiri, but in this case another approach was performed. Lactobacillus is known to have O-glycosidic chains, and so we took the gel band and performed a beta elimination, a reductive beta elimination treatment in order to release the O-glycosidic chains. And these O-glycosidic chains were hydrolyzed and analyzed by anion exchange chromatography. And so, I don't know if you see it, you can detect a peak corresponding to glucose as neutral components and a peak corresponding to galacturonic acid as acidic. We also analyzed reduced monosaccharides, and we could detect a peak corresponding to sorbitol, that is to say that glucose was the linkage between the oligosaccharide and the peptide. Then we performed a multi-mass spectrum of those oligosaccharides that were beta eliminated, and we could detect a peak signal corresponding to exuronic acid and exoses, 6 exoses, and 1 exitol, and also with 1 exos less, and also with 1 exuronic acid less, and 1 exos less, and so we could determine all the structure of the oligosaccharides by MALDI. But then we wanted to see where were these oligosaccharides linked to the peptide. And so we performed a trypsin digestion with the gel band. We performed a cotton helic chromatography in order to obtain an enriched glycopeptide fraction, and further on we analyzed it by ESI electrospray orbitrap, HPLC electrospray orbitrap. And although the whole run was very complex, looking into the the diagnostic ions, for example, for exocysts, we knew there were a lot of glucose, so we looked for the oxonium ions for exocysts in the MS-MS spectra, and we could detect a region here between set 5 to 15 or 12 minutes of the run that were the diagnostic ions of O-glycosid of exocysts. So we looked into this region and we obtained in the spectra at 5.6 minutes a cluster of ions with charge +3 that corresponding to this peptide that was in the known protein sequence, bearing 21 to 29 exos units. Very near, we would, at 5.6, we saw another cluster of ions, now with charge +4, corresponding to the same peptide, bearing also from 31 to 39 exos units. Of course, each of these were analyzed by MS-MS, and I'm just showing one example here. In the MS-MS of those, we could detect glycan fragments, peptide fragments, and glycan peptide fragments. That is to say, peptides, little pieces of the peptide with bearing the glycans. Further on, we continue the analysis, and we could detect at 10 minutes and to 15 minutes another cluster of ions, in this case +4, but it corresponding to the same peptide but with a miscleavage. This is a bigger peptide. But to that point, we couldn't find the galacturonic acid. And so we thought, just do it in the, well, in this case it was bearing also 28 to 35 exos. Well, just do it in the negative ion mode. And we performed the same spectrum, but in the negative ion mode, we could detect a cluster of ions with charge -4. And if you looked into between the major signals and the magnification, you can detect other signals that correspond to the same peptide with a miscleavage, bearing from 28 to 30 exos units and from 1 to 3 exulonic acids. So, up to this point, we could detect a peptide +3, +4, and the same with a miscleavage, +4 and -4, and all having each signal corresponding to different quantities of exoses and exoses with exulonic acid. There was another little peptide I'm not going to show you now. But when we looked into the sequence, we could detect that these lactobacillus have a lot of putative N-glycosidic sites. And N-glycosylation had not been determined in lactobacillus. So we looked into the HPLC ESI analysis and looking in this case for diagnostic ions of N-acetylhexosamine or N-acetylhexosamine without water, dehydrated. And we could determine that 3 regions where these diagnostic ions in the MS-MS were detected. So looking into these regions, well, on the other side, we perform a PNGS-F digestion of the shell and detect by anion exchange chromatography peaks corresponding to the released oligosaccharides. Well, this is the mass spectrum of corresponding to 7 minutes, 7.5 minutes, corresponding to this peptide, 233, 243 peptide containing the N-glycosidic sequence, and very near different glycoforms of the same peptide. Also, at 30 minutes, we could detect another peptide, nude and also bearing different glycosidic glycoforms. So, at this point, we could detect O-glycosylation, and for the first time, two sites of N-glycosylation pairing different structures. Well, we took then another lactobacillus strain in order to be sure it was possible that N-glycosylation was present in lactobacillus. And also it is another strain, and we could detect in this case diagnostic ions here in this region. And so we performed the PNGSF digestion of the shell band, and we detected by anion exchange chromatography complex M glycans. So in this case we did another approach. We took these complex M glycans and permethylated them, and analyzed the permethylated glycans by HPLC ESI mass spectrometry. And we could detect in this region the diagnostic ions of permethylated exos units and deoxyexoses. And so looking into the spectrum of these regions, we could obtain different glycoforms. The MS were very corresponding each part to a little part of these structures. And so we could detect there were N glycans and with very little, very small, and bearing the deoxyexoses in lactobacillus. Well, that was another approach. Permethylated glycans also analyzed by ESI, HPLC ESI mass spectrometry. And now the last another challenge was, are we able to analyze the whole glycoproteome? The proteomes, there are lots of works studying proteomes, but what about a glycoproteome? And so just to know if we can do it, we took the chicken egg white as a sample. We performed a precipitation with TC8 of the proteins, and we took these proteins and performed a trypsin digestion. And this trypsin digestion was enriched in glycopeptides, and this glycopeptide fraction was also analyzed by HPLC ESI mass spectrometry. And in this case, we could detect in the whole glycoproteome 27 proteins, but 9 of them were glycosylated. And the sequence, of course, of the chicken red white was taken from Uniprot database, and the proteins were identified by protein discovery. And then we could detect not only the glycosylated proteins, here they are, or transferrin, or albumin, or mucoid, that had not been determined before just in a glycoproteome analysis, but also the peptides, that is to say the N-glycosylation sites, and all the glycoforms, each of them pair in each glycosylated site. This analysis was performed using a semi-automatic homemade software, and also was checked with Bionic, that is a database. As we had determined in the whole proteomic pool the different glycoproteins, we wanted to know if we in this whole study we could lose some details referring to the isolated proteins. One type of analysis is to isolate the protein, for example, in the SDS page, and study that protein, and on the other side we had took all the proteins and studied all the glycoproteins in a batch. So we then isolated overtransferring in a shell we took the shell band corresponding to the molecular weight of the ovotransferrin and performed the same analysis. Perform the trypsin digestion of this band and analyze it by mass spectrum. And in this case, when we looked for the coverage of the protein, it was 80% coverage when the isolated protein was detected, was analyzed. And 80% of coverage was obtained when the glycoprotein was used in the whole glycoprotein analysis. So that was very, very interesting. It was detected in the same rate in both analyses. But in this case, when we analyzed the isolated ovotransferrin, we could detect two peptides, two codified peptides, and in one case we obtained 4 glycoforms, and in another case, in the other,